In this video cast, we'll take a look at sample problems from chapter 16, the first page. First, a couple definitions. Remember, acids are proton donors, and a proton is simply a hydrogen ion, because a hydrogen only has one proton and one electron. When you remove the electron and therefore give it a positive charge, all that's left is a proton. So H's are protons, and the acids donate them. Bases are proton acceptors. They take H pluses and accept them from acids. You can remember this because you can draw the B of a base, this is a B, B-A-S-E, as an H plus acceptor, or it eats H pluses. I call them proton suckers because they eat these H pluses right here. Those are bases. Now, there are also what are called the conjugates of the acid and the base. It's what's left over after the acid has released its proton or after the base has accepted a proton. So, for example, if we have HCl and we want to know its conjugate, it's what's left over after it's released the hydrogen, which would be Cl minus. This would be the conjugate base of the acid HCl. The same thing goes with a base. A base can have a conjugate acid to it. So for instance, if we have a base NH3, it's what is produced when it accepts or sucks a proton. And so the conjugate base of NH3 would be NH4 positive. This would be the conjugate acid. I'm sorry, I maybe said conjugate base there. This would be the conjugate acid of the base NH3. So let's take a look at the sample problems now, and a lot of these involve finding conjugate acids and bases and summarizing some of the strength things that have to go with acids and bases. First one, what is the conjugate base of each of the acids? So remember, the conjugate base is what's left over after the acid has released or donated its H plus or its hydrogen. So in HClO4, to find the conjugate base, release the hydrogen. What's left over? Well, ClO4, and since it lost the H plus, it now has a negative charge. So ClO4 minus would be the conjugate base. For H2S, release one of the protons, it would now be HS minus. Notice I only took one of the protons off of there. For pH4 plus, give away one of the protons, it becomes pH3, and since it had a positive charge, now it has a neutral charge, just pH3. For HCO3 minus, the conjugate base would be CO3 minus 2. Notice it goes from -1 to -2 charge because it released the proton. Those are conjugate bases. You should become very good at finding the conjugate base of an acid, and you should become quick at it. Next, what is the conjugate acid of each of these bases? So here's a number of bases, and remember, a conjugate base is what's produced when it accepts a proton. So for Cn minus, it would simply become HCN. It accepts a proton, bumps the charge up one, and now it becomes HCN, because remember, H has a positive 1 charge and this had a negative 1. For SO42 minus, tack an H onto it, it now becomes HSO4 minus 1. HSO4 minus 1 would be the conjugate base of SO4 minus 2. For H2O, if it acted as a base, it would accept a proton and it would become H3O positive 1. This is called the hydronium ion, by the way, and water, as we will see quite often, can act as an acid or a base. In this case, it's acting as a base and accepting a proton. And here we have HCO3 once again, just like we had it up above. HCO3 is one of those things that can also act as an acid or a base, and in this case, it's acting as an acid, and it would produce H2CO3, no minuses, I'm sorry, no minuses at all. It had a -1 charge right here, and now it will have no charge here, H2CO3. It accepted a proton, and therefore it became a conjugate acid. So let's look at writing some equations with acids and bases. Write an equation as HSO3 acting as an acid in water. So we need to write HSO3. We want to react it with some water, H2O. I like to write it as HOH because then you can see that this proton right here is going to be the one that's cleaved off and given away as an acid. Or you stick them together and then it can act as a base as well too. Your choice, you can write it as H2O as well. Anyway, it says HSO3 is acting as the acid, so it's going to be the one that's going to donate the proton to water, and in this case then it will form H3O plus, water accepting a proton and becoming positive, and then what's left over will be SO3 2 minus. Notice it was one less, and you can name the conjugate acids and bases from this as well. This was acting as the acid, so what's left over after that is called the conjugate base, and then this water right here accepted a proton, so it was the base, so this is the conjugate acid over here on this side. Next, write an equation as HSO3 acting as a base. So now we're going to have HSO3 acting the other way. So we'll write HSO3 minus and HOH once again. And this time it's going to act as a base. So HSO3 is going to be accepting a proton from water. So water is going to give away a hydrogen here to HSO3. So it becomes H2SO3 with no charge at all. Because remember, this has a positive 1 charge and it equals out this negative charge here. And then what's left over is oh, I'm sorry, I already did the SO3. The HOH released its proton, and so what's left over is the OH minus. It got rid of this proton right here, and now all that's left is OH minus. So to see the whole equation, you can see that HSO3 right here acted as the base. It accepted a proton from water, who acted as the acid. Since it accepted a proton, this is called the conjugate acid on this side, and OH minus here is called the conjugate base because it's what's left over after the acid H2O released its proton. Next, Li2O dissolves in water. When it does, it produces Li plus 2 ions and O minus 2 ions. It says the O minus 2 ion acts as a base with water. Write the equation. So we're going to take the O minus 2 ion. We're going to ignore the Li plus 2 ion. We're going to say that's a spectator and is not in this equation right now because it doesn't do anything. And in this case, it says it acts as a base, so it's going to be a proton acceptor. So water's going to give away a proton to O minus 2, and it's going to form OH minus. And what's left over of the water then is OH minus as well. And so we've got O2 plus H2O making the conjugate acid and the conjugate base, which really OHs make it be a super basic solution. And we'll find out later that O2 minus 2 is a super strong base actually as well. Next, list the strong acids and the cheer that go with it. And remember back in chapter 4 we talked about strong acids and strong bases and how those are the things that completely dissociate in water. And if you remember Hyber, Hickel, High, Hono, HNO3, Hickelo, HClO3 or 4, and then H2SO4. So the cheer that goes Hyber, Hickel, High, Hono, Hickelo, H2SO4. Simply you have to remember that there's is HClO3 or HClO4, and then you're good to go. Okay, remember that those are the strong acids and they completely dissociate in water, and that's what makes them strong. Not that they're concentrated. They can be concentrated or dilute, but whatever is dissolved in water completely breaks up into ions. So, using those ideas, summarize the relative strength of the following conjugate acid-base pairs. So here we have HNO3 and NO3 minus. And as we saw in the video cast before, if something is a strong acid, like HNO3 is right here, its conjugate base, after it's released the proton, is super duper weak. As a matter of fact, it has negligible basic properties. And so we can say that HNO3 right here is a strong acid, and we can say that NO3 is pretty much a non-base, or a super weak, I can't write enough weaks, base. Because they act in a pair. If one's strong acid, then the base is going to be super duper weak. So take a look at H2SO4 and HSO4 minus. Once again, we have a strong acid right here in H2SO4, which means that its conjugate base, what's left over after the acid has released its proton, is going to be super weak. So we can say that it's a strong acid to start with, and then actually HSO4 minus is such a weak base that it actually acts slightly acidic. And we'll see later on in the chapter that there's a rating way numerical rating way, and we'll find out that HSO4 minus actually has a decent amount of acidity properties to it. So H2O and OH minus. Now H2O, of course, is neither a strong nor a weak acid or a base. In this case, it's releasing a proton, and then OH minus becomes its conjugate base. So we have to say that it's a really weak acid to start with. It gives away its proton, and what's left over is a decent base, a decent strength base in OH minus right here. HBr and Br minus, once again, HBr is a strong acid, and then Br minus here, of course, is going to be a non-entity, a super weak base. Okay, so watch for that. Remember, if you have a strong to start with, the conjugate is going to be extremely weak. If you have a weak to start with, you're going to end up with a decently strong base. Next, write the equilibrium constant expression for the autoionization of water, which is also called the ion product constant. So here we take water and we react it with water. And remember, as we learned in our last video cast, water reacts with water on a very limited basis, but it does react, and a tiny bit of it will form this acting as an acid and giving it away to HOH here, forming H3O plus, and then what's left over after it releases its proton is OH minus. So we'll have HOH plus HOH makes H3O plus OH minus, and if we were to write the equilibrium constant expression for this, it would be K is equal to products H3O plus times OH minus its concentration divided by the reactants. But you see the reactants right here are pure liquids, and remember, pure liquids and pure solids don't go into the equilibrium constant expression. So this would be the expression for what is called the autoionization of water, and instead of calling it K sub C because it's in terms of concentrations of H3O and OH minus, we now rename it and we call it KW or KW because it is for water's ionization. This actually has a very constant value at 25 degrees Celsius. It is equal to 1 times 10 to the negative 14th. Remember, we can change KW or any K by changing the temperature, but as long as we're at 25 degrees Celsius, which is kind of standard temperature for thermodynamic things, we're going to have it as 1 times 10 to the negative 14th, which means that only like 1 times 10 to the negative 7th is going to be present in molarity for each of these, which is not very much. Calculate the concentration of the OH minus concentration in a solution in which, and now they give us some variables here, and we're going to use this equation that we just developed right here, the equilibrium constant expression for the autoionization of water. So in this aqueous solution, we've got H plus equal to 2 times 10 to the negative 6th. And so we could plunk that into the KW equation, where we'd say 1 times 10 to the negative 14th is equal to the H plus ion concentration of 2 times 10 to the negative 6th times the concentration of OH minus. And we could solve for OH minus by dividing both sides of the equation by 2 times 10 to the negative 6th. Now, to put this in your calculator, if you want to follow along with my old-fashioned TI-83, the best way to do this is type in 1 and then hit your enter exponent key. It'll put an E on the screen, and then type in negative 14. So negative sign 14, and then divided by, and our number here is 2 times 10 to the negative 6. So 2, enter exponent, negative 6th. And then go ahead and hit enter, and we find out that we have 5 times 10 to the negative 9th, 5e negative 9. So our answer for the H plus ion concentration in letter A is 5 times 10 to the negative 9th. And if you want to write it this way, that's okay. Or 5 times 10 to the negative 9th is probably the more mathematically accepted way as well. Okay, letter B, H plus is equal to OH minus. Well, now we have the two equal to each other. Well, I'm going to do this one on a separate piece of paper. just so we can see it a little bit better. Here's our numerical values, H plus equals OH minus. So what I could write is 1 times 10 to the negative 14th is equal to H plus times OH minus. And since these two are equal to each other, if I called one of them X, well, I'd call the other one X as well. So I'd have X times X is equal to 1 times 10 to the negative 14th, which is actually saying I have X squared equal 1 times 10 to the negative 14th. Well, that's not hard to do on my calculator. As a matter of fact, you might be able to do that one in your head, because if you're going to square root both sides of the equation to get X, what are you actually doing to this? You're taking it to the 1/2 power, right? And when you have something taken to the 1/2 power, you're actually just multiplying this exponent by the 1/2 right here. And what's 1/2 of 14? 7, right? So the answer is that the H plus, which is equal to the OH minus, is equal to 1 times 10 to the negative 7th. Lastly, in letter C, H plus is equal to 100 times OH minus. Well, this one might take just a tiny bit more thinking. So let's take another piece of paper and put it right above here. And in this case, we can use our equation H plus times OH minus is equal to 1 times 10 to the negative 14th. And it wants us to find the concentration of OH. We can see that we can put H plus as being 100 times OH minus, and we could write that into this equation right here and replace H plus, or substitute H plus with 100 times OH minus. Leave this OH minus the same, and that's equal to 1 times 10 to the negative 14th. Look, I've got two things that are the same. I can multiply those together now, and now I have the equation 100 times OH minus squared is equal to 1 times 10 to the negative 14th. Divide both sides by 100, and then square root both sides. And dividing by 100, remember, is also the same as saying 1 times 10 to the second. So if we subtract that from there, we can do it on our calculator as well if you'd like to see it. We'll take 1, enter exponent to the negative 14th, and we're going to divide it by 100. And then you can take the square root of that, which remember is just taking this exponent and cutting it in half. Or if you want me to do it, I can put square root sign, second answer from up above, and we end up with 1 times 10 to the negative 8th. 1 times 10 to the negative 8th. So OH minus in this case turns out to be equal to 1 times 10 to the negative 8th. Last problem on the page. Determine the H plus with the solution. These are very similar to these problems, except for now you're solving for a different variable. Let's just jump to letter B. Letter B says OH minus is equal to 1,000 times H plus. So now in our equation, H plus times OH minus is equal to 1 times 10 to the negative 14th. I can plug in the numbers 1,000 H plus for OH minus. So I'll have H plus times 1,000 times H plus is equal to 1 times 10 to the negative 14th, just like I did the substitution up above. I can group these terms, and now I have H plus squared is equal to 1 times 10 to the negative 14th divided by 1,000. And if you want to do this on your calculator, we can do 1, enter exponent to the negative 14th divided by 1,000 is equal to, and then notice I need to take the square root of both sides once again once I have that. So second square root, second answer, and I end up with 3.16 times 10 to the negative 9th. 3.16 times 10 to the negative 9th as my concentration of H plus.